the linear vector space linearly independent vector linearly independent vector dimension of vector space basis of vector space. So friend, as you know, the Schrödinger equation is one of the cornerstones of the theory of quantum mechanics, as it has the structure of a linear equation. The formalism of quantum mechanics deals with the operators that are linear and wave functions that belong to the abstract Hilbert space. The mathematical properties and structure of Hilbert space are essential for a proper understanding of the formalism of quantum mechanics. Quantum mechanics, as you know, was formulated in two different ways by the Schrödinger and Heisenberg. The Schrödinger wave mechanics and Heisenberg's matrix mechanics are the representations of the general formalism of quantum mechanics in continuous and discrete basis system, respectively. For this, we learn about the basic mathematical tools in terms of the linear vector space, the Hilbert space, and related numerical problems. So, friends, let's start the video lecture. You are watching the Sai Academy YouTube channel. If you like this video, please share this with your friends. And if you are watching this for the first time, subscribe the Sai Academy channel so that you get the notification for the upcoming videos. So friends, let's start the lecture. So the linear vector space. A linear vector space consists of two sets of elements and it follows two algebraic rules. A set of vectors like psi, phi, and some sets of scalars A, B, C, and so on. These scalars may be real or complex, and it follows rules, that is vector addition and rule for scalar multiplication. So under addition rule, it has some properties and structure of an abelian group. So vector space must be an abelian group, that is, if psi and phi are two vectors of a space, then their sum psi plus phi must be a vector of the same space. It should follow the commutativity, that is, psi plus phi should be equal to phi plus psi. It should also follow associativity, that is, that is if there are three vectors psi, phi and xi, then psi plus phi plus xi should be equal to psi plus phi plus xi. That is, it should follow the associativity principle. And there is an existence of a null vector or a zero vector, or sometimes it is called neutral vector. For each vector psi of the space, there exists a zero vector such that zero vector plus psi vector is equal to psi vector plus zero vector is equal to psi. Similarly, there is an existence of a symmetric or inverse vector. That is, for each vector psi, there must be an inverse vector minus psi such that psi plus minus psi is equal to minus psi plus psi is equal to zero vector. Further, the linear vector space also follows multiplication rule, which have certain properties as given below. Multiplication rule. So for a vector space to be linear, the multiplication rule should have these properties. First is the product of a scalar with a vector should give another vector. That is, if psi and phi are two vectors, then any linear combination a psi plus b phi is also a vector of the vector space, where a and b are scalars. Under the multiplication rule, it should have the distributive distributivity principle with respect to addition, such that a scalar multiplied with the addition of two vectors psi and phi is equal to a psi plus a phi, and if there are two scalars addition multiplied with the a vector of the vector space, then it should have the distributivity rule as a plus b into psi is equal to a psi plus b psi. Further, obey the associ- it should obey the associativity principle with respect to the multiplication of scalars. That is, a into b psi is equal to a b into psi. And next is the for each element psi under the multiplication rule, there must exist a unitary vector element I and a zero scalar such that I into psi is equal to psi into I is equal to psi, and zero vector into psi is equal to psi into 0 is equal to 0 vector. So friends, if these two rules, first the addition rule and second the multiplication rule, are followed by the vector space, then it is a linear vector space. Thus, the linear vector space forms an abelian group under the two rules, addition and multiplication. If we restrict to real multipliers, we will obtain a real space, and if the multipliers are complex, then we will get the complex vector space. Now we will learn about the linearly independent vectors. Let us consider a set of n vectors such that phi1, phi2, phi3, dash dash, phi n. So these are the vectors and it is said to be linearly independent if and only if and only if the solution of the equation summation I is equal to 1 to n ai phi I is equal to 0 gives a1 is equal to a2 is equal to a3 and so on an is equal to 0. That is all the multiplier that is all the multipliers are 0. Now suppose if there exists a set scalars which are not all 0 and one of the vectors can be expressed as a linear combination of the other vectors. Then in that case, phi, a vector can be expressed as a linear combination of ai phi I summation I is equal to 1 to n, where sum ai not equal to 0. Then the set of vector phi I is said to be linearly dependent vector space. Now we'll learn about the dimension of a vector space and the basis of a vector space. So let's see. The dimension of a space vector is the maximum number of linearly independent vectors that the space can have. For example, if the maximum number of linearly independent vectors that a space has is n. That is the total number of linearly independent vectors are phi1, phi2, phi3 and so on phi n. Then this space is said to be dimensional vector space. In this case, any vector psi of the vector space can be expressed as a linear combination of another vector phi I such that psi is equal to summation I is equal to 1 to n component ai into phi I, which is certainly equal to a1 phi 1 plus a2 phi 2 ai phi. Now we'll learn about the basis of a vector space. As we know that the maximum number of linearly independent vectors of a space is the dimension of the space, and in that case it can be expressed as the another form of another vector. Now these maximum number of linearly independent vectors form a set, that is linearly independent vectors is n, that is phi 1, phi 2, phi 3 and phi n. So these vectors are linearly independent and they form a set phi. So the basis of a vector is a set of the maximum possible number of linearly independent vectors. So this set phi I will be the basis of a vector space and it is denoted by the set phi I. And these vectors phi 1, phi 2 and phi n are called the base vectors. Although the set of these linearly independent vectors is arbitrary, it is convenient to choose them orthonormal, that is, their scalar product satisfy the relation phi I phi j is equal to delta ij. So if phi I and phi j are same, then phi I and phi I will give 1, and if I is not equal to j, in that case it will give 0, and when I is equal to j it will give 1. The basis is said to be orthonormal if it consists of a set of orthonormal vectors. The basis is said to be complete if it spans the entire space. That is, there is no need to introduce any additional base vectors. In that case, basis will be said to be complete. The expansion coefficient A1, A2, A3 are called the components. A1, A2, A3 are called components of the vector psi, and each component is given by the scalar product of the psi with the corresponding base vector. For example, Aj can be given as the scalar product of phi j in and psi. The example of the linear vector space is the three-dimensional Euclidean vector space. The basis of this space consists of three linearly independent vectors denoted by, as you know, I, J, K. And any vector of the Euclidean space can be written in terms of these base vectors, such as any vector A in the Euclidean space can be written as the A1 I plus A2 J plus A3 K, where A1, A2 and A3 are components of A vector in the basis, and each component can be determined by taking the scalar product of A with the corresponding base vector, such, such that A1 can be obtained by I in dot vector A, and A2 component can be obtained by scalar product of J into A, and similarly A3 can be obtained by scalar product K and A. It is important to note that scalar product in the Euclidean space is real and hence symmetric, and norm in this space is usually gives the length of the vectors, that is, also it is to be noted that whenever A1 I plus A2 J plus A3 K is equal to 0, we have A1 is equal to A2 is equal to A3 is equal to 0, and in that case norm of the unit vectors IIJ can be expressed as a linear combination of the other two. So this is for now. I hope you like and enjoy this video lecture. So share this video with your friends and subscribe this Sai Academy channel so that you get the notification of the upcoming video lectures. In the next video lecture, we will be learning about the Hilbert space and its different properties. Till then, stay tuned. Thank you. Bye.